Welcome to The Explainer. Okay, get this. There's a scientific technique that can link a criminal to a crime scene with just a microscopic trace of evidence. And it can even help diagnose diseases years before any symptoms show up. It's all about the art of separation.
So let's say you're trying to solve a crime. Your key piece of evidence, maybe a trace of poison or a drop of ink, it's completely, invisibly blended with dozens of other substances. How in the world do you isolate just the one thing you need? For forensic scientists, doctors, and chemists, this isn't just some thought experiment. This is their reality, every single day. And solving it is absolutely critical. The answer is a technique that lets us untangle these incredibly complex mixtures, literally molecule by molecule.
Now, the answer to this puzzle began over a century ago, and it all started with a simple but totally brilliant observation about plants and a scientist who was just determined to understand the colors of nature. So this is the guy, Russian-Italian botanist Mikhail Tsvet, and way back in 1903, he was fascinated by a pretty simple question: what makes green leaves, well, green? He had this hunch that there was more than just one pigment in there, and he really wanted a way to pull them all apart. So what he did was actually pretty ingenious. He packed his glass tube with powder and then poured a solvent with leaf extract through it. As the mixture traveled down the tube, something amazing happened. It separated out into these beautiful, distinct colored bands. You had green chlorophylls, orange carotenes, and yellow xanthophylls. He called his new technique color writing, or as we know it, chromatography. The principle behind this is surprisingly simple. You might have even done this in a science class. You just put a dot of black ink on a piece of paper, dip the edge in a solvent like water, and then you watch as that solvent creeps up the paper. That single black dot starts to separate into this whole rainbow of its component dyes. It's basically a race. Okay, so what's the magic here? How does this race actually work? Well, it all comes down to two key players. First, you've got this stationary phase. In our example, that's the paper. Think of it as the obstacle course. Then you have the mobile phase. That's the solvent, the runner that carries the mixture along. Each different colored dye in the ink has a different chemical attraction to the paper versus the solvent. The dyes that are more sticky to the paper obstacle course move slower, while the ones that dissolve better in the solvent runner travel further and faster. Simple as that. All right, so from a simple piece of paper and some ink, let's jump forward to today, because that simple race has been completely transformed into a high-tech analytical powerhouse that scientists rely on. Scientists have basically taken Tsvet's core idea and put it on steroids. We're talking about incredibly sophisticated machines that run this race way faster with way more precision and on a microscopic scale that can separate even molecules that are almost identical. So in the modern lab, you've basically got two main workhorses. First up, there's gas chromatography, or GC. For this one, the mobile phase, the runner, is actually a gas. This makes it perfect for separating volatile stuff, things that turn into vapor really easily. A great example is analyzing the flammable liquids an arsonist might have used. Then you've got high-performance liquid chromatography, or HPLC. This uses a high-pressure liquid to separate bigger compounds that don't vaporize easily, like most prescription or illicit drugs. So now that we have these incredible tools, what can we actually do with them? Well, this is where it gets really interesting. We're talking about solving puzzles that were just completely impossible before, from the crime scene all the way to the doctor's office. In forensics, this stuff is an absolute game changer. It can analyze the tiniest, almost invisible organic compounds left behind in gunshot residue. Here's the cool part. Every type of ammunition has its own unique chemical fingerprint. Chromatography can match the residue on a suspect's hand to a specific bullet, creating a crucial, undeniable link in an investigation. And when you get to toxicology, the sensitivity is just mind-blowing. There's a version called ultra-high-performance liquid chromatography that is so powerful, it can detect tiny, tiny quantities of drugs, like the synthetic drug known as pink cocaine, that have actually been incorporated into a single strand of hair. This lets toxicologists build a whole timeline of a person's drug use over weeks or even months. But it's not all crime and drugs. The potential in medicine is, honestly, it's incredible. Right now, researchers are using gas chromatography to analyze the unique volatile compounds on a person's skin. They found that the subtle metabolic changes caused by Parkinson's disease actually create a specific scent profile. And this opens the door for a simple, non-invasive skin swab test that could diagnose the condition years before physical symptoms ever show up.
Just amazing.
So, where does this incredible technology go from here? Well, the race is definitely still on. Scientists are pushing to make it even faster, even smarter, and way more accessible than ever before.
The future is really pushing in a few key directions. First, you've got AI jumping into the mix, sifting through massive amounts of data to identify unknown compounds in minutes instead of days. Then, everything is getting smaller. We're talking portable, miniaturized devices that can bring the power of the lab right to the crime scene. And of course, the hunt is always on for even greater sensitivity, and there's a big push for green chemistry, methods that use fewer harsh chemicals and are better for the environment. It's pretty amazing when you think about it, right? We went from a botanist just being curious about why leaves are green to a technology that solves crimes and diagnoses diseases. It just goes to show you that sometimes the biggest answers are found simply by pulling things apart. So the only question left is, what other secrets are just waiting to be separated?